this video is going to be all about rotational kinetic energy. So in the world of physics that we talk about, there are two kinds of kinetic energy, which I'm going to abbreviate as KE. So the first kind is the one that we are most familiar with. It is the linear, or sometimes called translational, kinetic energy, right? And that occurs when we have straight line motion. So your typical like ball rolling across a floor, car moving on a street, anything like that. And we calculate that kinetic energy, which I'm going to write as KET since we're talking about two kinds in this video. We calculate that by doing 1/2 the mass times the speed or velocity squared. Okay. The other kind of kinetic energy that we can talk about is the rotational kinetic energy. Okay. And we have that whenever we have rotation or even circular motion. Right? We essentially need to rotate around some central point. Okay. So anytime we have an object doing that, it is going to have rotational kinetic energy. And we calculate the rotational kinetic energy by doing 1/2 I omega squared. As a reminder, I is rotational inertia, sometimes called the moment of inertia, and omega is the angular velocity. Okay. As a quick aside, remember that the rotational inertia or moment of inertia measures mass distribution. So is the mass close to the axis of rotation, or is the mass farther away from the axis of rotation? Okay. We can combine these two motions, linear and rotational, into rolling motion. Okay. So that would actually be a combination, like I said, of linear and rotational. Okay, and we can have rolling motion or linear and rotational kinetic energy if we're thinking about just an object. Okay, so an object that would have rolling motion would be a ball rolling downhill. Okay, so in that instance, the gravitational potential energy is going to convert into rotational kinetic energy and linear kinetic energy. Okay? Or if we have more of a system that we're thinking about, we might have a pulley with a mass hanging off of it, and as this mass falls vertically, the pulley begins to rotate. Okay? So in that sense, we would have the gravitational potential energy of the mass, meaning this hanging mass, converting to rotational kinetic energy of the pulley and linear kinetic energy or translational kinetic energy of the mass. Okay. Now, on the AP exam, they do this very conceptual treatment of rotational kinetic energy. The likelihood of you having to do math with this is very slim, especially with the new AP exam. Okay, so the one thing that I really want to focus in on is this ball rolling downhill. Okay, so let's say we have 3 different hills and they are all the same height, but I can't draw, so they look different. Okay, this first one is frictionless and we have a block sliding down. These last two are non-frictionless because this one has a hollow sphere rolling down, and this one has a solid sphere rolling down. And remember, we need friction to create the torque in order to be able to roll. So that's why I can't say these last two are frictionless. Okay. And what we might be asked to do is compare linear speeds at the bottom. Okay. So in all of these instances, let's all say they all have the same mass too, just to keep life simple. Okay. So they all have the same mass, which means we all start with the same gravitational potential energy because we have the same mass and height. Okay. Now, from that, if we were just thinking of like beginning of the year kinetic energy, we might automatically think that they all end at the same speed. But that is not the case anymore. Okay, so this first object here, let's label this A, B, C. Okay, so in situation A, all of that gravitational potential energy is going to convert, that's what that arrow means if you ever see it in the videos, is going to convert to translational kinetic energy. Since there's no friction, no nothing, and this is because energy is conserved. Okay. In B and C, all of that potential energy is going to convert to not only translational kinetic energy because we're moving down the inclines, but also rotational kinetic energy because these objects have a torque that will create or allow them to roll. Okay, so we have to split, okay, we're splitting the gravitational potential energy between the translational and rotational kinetic. It's not an even split necessarily, but it's there, okay? So that tells us that A will have the largest speed because it has the most translational kinetic energy because there's no sharing with rotational kinetic energy. Okay. So now we have to decide between B and C. And the difference between B and C is that one is hollow and one is solid. Okay. Remember, hollow objects have larger I values because the mass is distributed further from the axis of rotation. Okay. That larger I value, so let's see, B has the larger I value, which means it has more rotational kinetic energy than A, so less translational kinetic energy, so B moves slowest. Okay. And A, or C, rather. Oh, this should be K-E-R than C. Whoopsies. So that means that C is in the middle. So A moves the fastest because all of that initial gravitational potential energy converts to translational kinetic energy because energy is conserved. Okay. B moves the slowest because we have to split between translational and rotational. Since B has that larger moment of inertia because it's hollow, it has more rotational kinetic energy, so there's less translational kinetic energy, so that means B has less velocity. And that's basically what you could expect the AP exam to test you on when it comes to rotational kinetic energy. It's kind of that ball rolling downhill, right? And that's it for this video.